So our second speaker, I'm very pleased to welcome our second speaker, Renaud Nicolaÿ. He is professor of organic and inorganic chemistry at ESPCI Paris and director of the Macromolecular Chemistry and Materials Institute. He received PhD degrees from Pierre and Marie Curie University in 2008 and Carnegie Mellon University in 2009, working under the supervision of professors Patrick Emery and Chris Maciejewski. In 2010, he joined the group of Professor Bert Meyer at the Eindhoven University of Technology as a postdoctoral researcher. Later that year, he joined the ESPCI Paris as assistant professor. He led the chemistry and macromolecular design team within the T3M laboratory from 2019 to 2023. The research activity of his team aimed to develop new synthetic methodologies, as well as to design responsive formulations and high-performance recyclable materials. Renaud, we are very happy to have you here today. Thank you for joining us. It was difficult to manage it. You succeeded. Thank you very much. It's a real pleasure to have you. So, the floor is yours as soon as, but yet, is close to be yours. Thank you.
I can start without the slides by thanking the organizer and thanking especially you, Sylvain and Vincent, for the invitation, for allowing me to be here. Really a pleasure to interact with colleagues face-to-face. I'm not a big fan of video conference, so even it was a bit challenging. I'm very happy to be here. I enjoy very much direct interactions. And so today, my presentation will be a bit less didactic than the presentation of Jean. I'm going to go a bit faster to some specific, it's not a literature review. So I chose to focus on a few examples, most of them being from our lab, but not starting with this. And normally I should not finish because it's always too long, even though I was told that I can keep the lunch or the lunch break. And with this, wait for the slides maybe.
Thank you, Renaud. It's coming up, I think.
It's okay. So the talk will be about, so maybe I can introduce our lab. So I'm working in Paris. Our lab is called ICGM, and it's composed of molecular chemists, polymer chemists, and physical chemists and physicists of soft matter. So we like to go from small molecule to polymers. And today, to fit within the workshop, I will be focusing on the polyethylene, cross-linked by reactive processing. Okay, thank you. So since it will be too long, or it should be too long, I will start with the acknowledgement. This work is something that most of the research work will be from our team, CDM team, which is now led by Nathan Vanzi, who is a CNRS researcher, and we collaborate in a lot of projects. So Nathan joined the CNRS very recently, and I hope that if some of you are still interested to join academia, be aware that we are a small lab in Paris looking to recruit new researchers. And the experimental work was done by Thomas Vialon in the framework of his PhD. Wilson, who is continuing this work, a PhD, and Paul Gaglianopoulos and Georges Formont were involved in this work during their postdoc. And it's a highly collaborative work. We collaborate a lot with Johan Guyneuf from ICR in Marseille to conduct EPR at high temperature and to do some calculation. And we also collaborate with colleagues from Paris, Marie-Noëlle Rager for advanced NMR characterization. I'm not going to discuss it today, but we did a lot of nitrogen-15 NMR, which tends to be quite challenging, and also colleagues from Sorbonne University for EPR, for SAX measurement, and for Raman spectroscopy. So there are a lot of characterization. Not all of it will be covered today. So I will start with a small discussion about recycling, and I'm going to discuss only mechanical recycling in the frame of this talk, not chemical recycling. And as Jean mentioned, we produce a lot of plastics, more than 400 million tons per year. Most of them are fossil-based, as Jean showed. And in fact, Jean was even too optimistic because 90% is fossil-based, 9% is recycled, 1% is biosourced. But the 9% which are recycled, they are also fossil-based. So we use a lot of fossil to do this. And when it comes to plastic production, we cannot, I'm not going to do it today, but I will still say this way, we cannot discuss this without thinking about the oil production. We drill to extract oil, and we use this oil to add energy, to move, and part of this is used for chemistry. They are linked. So a question we can ask ourselves is, do we make that many plastic because we need it, or do we make that many plastic because we need to use the oil or the chemicals which are extracted? I don't have the answer. I have an opinion, but I don't have the answer. So when it comes to plastic, they are incompatible, thermodynamically incompatible, even when they are very similar, such as P and PP, as we discussed. So they don't like to mix, and if we give them enough time and energy to do this, they will phase separate. And at the interfaces, there is no entanglement, and Jean mentioned the necessity to have entanglement of good mechanical properties, and we end up with material with very poor properties. So we need to source plastics, and as of now, plastics are extremely inexpensive. Sorting has a cost. So in our society, which is very much profit-driven, this is not interesting at this stage. So we need to sort them, and even when we sort them, their property tends to degrade because of side reactions, such as beta scission for polypropylene or for metacrylic base, or undesired cross-linking for P, for example. One will decrease the mechanical properties, beta scission, the other will decrease processability. Cross-linking will decrease processability. So we end up with a material which is more expensive and with lower properties. So this is probably the main reason that we don't recycle plastic better, because many solutions already exist, and this I came to realize very recently. And this is what Jean mentioned at the end of his talk about chemical recycling. I think currently it's not a technological problem. If we think about polyolefin, and as you said, we take polyolefin, we do pyrolysis, we go back to a crude wax, and we can either use this wax, but if not, we just do the cracking and we go back to the monomer. So the solution is here. It's just a question of cost, and we have to think about this as academics when we draft our project, because sometimes we are ignorant of solutions that do exist already. So when it comes to polyolefin, as it was said, they represent approximately half of the plastic produced, a bit more, a bit less, depending on the number. And PP, high-density polyethylene and low-density polyethylene, even though they are very similar, they are incompatible. And what is really sad, I would say, is that these are among the least recycled plastics for different reasons. We produce them the most, and they are the least recycled, partially based on the application we use them for, which is packaging and even short-term packaging. So this is a real problem, and I would say a bit naively, we jumped in it. And before going there, I would like to restate or emphasize what Jean introduced. So we have the structure of PE and PP. They look very much the same. They have pretty similar density. So the way plastic are sorted, they are sorted in different ways. One of them is density. So in like a sorting facility, we can use infrared to sort plastics through their composition. It's very efficient. And they cannot be really easily sorted by infrared. And we also use density. And we sort polymers with different densities. These two, they are difficult to sort. They can be sorted, but often we need 2 cycles of sorting, which has a cost. And the thing is, even though they are very similar, here you have a TEM image, transmission electron microscopy image, of a major phase of PE and a minor phase of PP. And you can see that we have domains of PP and they are incompatible, as I said. And the problem is that at the interface, as you can, it is shown here with this schematic, there is no entanglement between P and PP, or very limited. And because of this, there is no transfer of the mechanical strength and the very poor mechanical properties. And among the things which are interesting with polyolefins, so here you have a graph which represents tensile testing of PE, PP, and the blend. So here you have the tensile stress, in megapascal. Here you have the tensile strength in percent. And P and PPs are really amazing materials because they can be easily processed. They are currently extremely inexpensive. Their synthesis has been optimized in amazing ways. And they are very good mechanical properties. They can be tough and they can be ductile. So you may need to provide an important stress to deform them if you want, because if you don't want this, you just go to low density PE. But then you have ductility, so they can deform a lot before they break. So this is pretty amazing, I would say. And so in blue, you have PP. This is a commercial grade, nothing special. In black, you have, no, sorry, in blue, you have P, I apologize. In black, you have PP. So PP is a bit more, has better mechanical strength. Both of them are highly ductile. And if you blend these two materials, even without doing anything else, so they were not aged, they did not suffer any kind of degradation, took them from the bottom, we just blend them, you inject them to get the dog bone, and then you go from a ductile material to fragile material. So this is an exemplification of the problem we have to deal with. And so when it comes to mechanical recycling of polyolefin, it's very much based on compatibilization of these two materials or compatibilization and or improving the interface. At this pace, I'm really gonna be, have to cut my presentation short, but it's better like this. So how it can be done? You can use non-reactive compatibilization. So the idea here, it's a combination. So it's to lower the interfacial tension, so to make these two objects more compatible. And like this, we can also stabilize the face which is dispersed in the other one. But I would say when it comes to mechanical properties, it is mostly to be able to transfer the stress across the interface. And here you have in blue, you have PE, in gray, you have PP, and tough to see here, but here in the darker, there are copolymers, which have a good affinity for PE and a good affinity for PP. And they, in fact, they provide entanglement. And ideally, the best solution is that they provide entanglement, and if they can co-crystallize, then you really improve the mechanical property. So the ideal system probably would be to be able to have co-crystallinity in both phases, because this is how you will improve probably the best of the properties. And another solution is reactive compatibilization. So in this case, it is based on physical interaction, co-crystallization mainly, but you can also think about van der Waals interaction, the kind of polyolefin. Reactive compatibilization is to create chemical bond at the interface, and this chemical bond will allow to transfer the stress. So one way to do this is to create in situ block copolymers. So I will show you one example of the two. So, and this is very much related to what Jean presented. Not so long ago, there was a very nice publication by the group of Jeff Coates and Frank Bates and Bob Lapointe, where they were able, using an hafnium catalyst, so there, in fact here, there was a huge development about catalysis. Using a catalyst, hafnium catalyst, they were able to make multi-block copolymers of P and PP, isotactic PP, as you understand now, that's pretty important. And they were able, this was probably the breakthrough, to have multi-blocks, not only diblocks, but also triblocks, pentablocks, and also very long blocks. And what they did, they studied the ability of these multi-block copolymers to compatibilize P and PP and to improve the mechanical properties. So they showed this with lap shear tests. So you have, here you will have PE, here you will have PP, and they put in their copolymer at the interface and measure the adhesion mechanical property. And they have, it's a very nice paper, so I really invite you to read it if you did not do it. They went from short die block to long die block and to tetra block, long or short. And what they propose is what I mentioned briefly, that it is very important to not only have entanglement in the amorphous phase, but to have co-crystallization. So this is, I think, one of the take-home message. And here you have TEM. So this is TEM of the blend of P and IPP, 70-30, the same I showed you. So a strong phase separation, a very fragile material. And by adding block copolymers, I'm not going to cover all of them, they were able to go back to something which is a material with very good mechanical properties, which is ductile. So this is very efficient, no need for chemical reaction. If we would have to try to point toward something that could be improved, it's not so easy to make these block copolymers, and they are specific of the blend you want to recycle. So another option is to do a reactive compatibilization, and I will give you one example. So in this case, we want to create bond at the interface during the processing, ideally. So this is, if you can do this by reactive processing, no need for a solvent. And ideally, you would like to not to change the process which was used to process the plastics. So here, for example, you have a polyethylene, which is terminated by a carboxylic acid function. You have a polystyrene with an oxazolene function, and you can react the carboxylic acid on the oxazolene, and you create this amide bond, and you can connect the P and the PS, and you make in situ the block copolymer, which will be your surfactant, which will be used to improve the compatibility or to decrease the interfacial tension. And here you have SEM image, and you see you can go from a big object to something which is much better dispersed. So this is an indication, one of the ways you can observe this, of the increase of the compatibility by the reduction of the domains of the dispersed phase, just a surfactant effect. So in this case, what is interesting is that it cannot be much easier to make the block copolymer. They are made in situ, and it can potentially be versatile. But I think there are a lot of challenges with this approach. We have to make the functional polymers. It's not always easy, as it was said. It's not so easy to make functional polyolefins. And this reaction has to be compatible with the processing condition and all the chemicals you may find in your blend to be recycled. So it's pretty challenging, but this is a line of research we are interested in, and I will discuss on this. So not directly connected to this, but something that we did in the lab, and we are not the only one, and I really would like to emphasize, I don't pretend to make a literature survey. So now I will be focusing much more on things coming from our lab, but there are a lot of very nice examples, many of them much better from other labs. So what we did, really linked to this, we made a P which was cross-linked with this type of function, dioxoborane. And what is very interesting with dioxoborane is that if you take two dioxoborane, they can undergo a metathesis reaction to reshuffle the partner. So you can exchange the partner which is linked to the bond with partner which are linked to the diol part, and you make a blend of this molecule. And what is very nice is that the boron-oxygen bond and the boron-aryl bond are both very strong. They are thermally resistant, they are not sensitive to oxidation, and this exchange can take place without the need for a catalyst. So it's pretty interesting if you want to go to reactive processing. If you would like to do dynamic current chemistry in water, this is for sure not a good idea. So take home message here is that dynamic current chemistry, you need to find a good one for what you would like to do. I don't think there is a dynamic reaction which is good for everything. But in our case, it's pretty interesting. So we take a P which is cross-linked with these dynamic bonds. We take a PMMA which is crossing with the same bonds, and when we put them into contact, we can hope to create a chemical bond at the interface between PMMA and P. And this was done qualitatively with a lab shear experiment, a bit similar to what I showed you. So HDP was prepared, cross-linked with this bond. PMMA was prepared, cross-linked with this bond. We put them into contact at 190 degrees Celsius without any kind of treatment of the surface, nothing. And then if you wait long enough, in our case, 10 or 20 minutes, this was clearly not optimized, and you do the lab shear test, the adhesion at the interface between P and PMMA is so strong that we always break in the bulk of PMMA. So this is an indication of the creation of a strong bond. And what is really interesting is that you can make this crossing P by reactive processing too. And this is something that we worked a lot. So this is something that was done at the former C3M lab, LMC lab, and this is a continuation of the initial work of Ludwig Leiber and François Tourniac on Bitrumer. So with Ludwig, we show that we can transform PE by reactive processing, for example, using a bis-maleamide with a bis-dioxoborane in the center, using radical cross-linking, radical grafting with a dichromate peroxide. Through reactive extrusion, we can go toward a material which we call a Bitrumer, which is a chemically crossing material, which is still processable. So my message here is that we can get to these objects here through reactive processing. So we can potentially create them during mechanical recycling of the plastics. And in fact, we are not the only one to have this idea. And as often, we were for sure not the fastest. And I will show you 3 examples of very interesting work on this. This one is from the group of Shipping One in California. So they work with a different exchange chemistry, siloxane exchange using fluorine anion. So here I think it's a good, I should be very careful when I speak about fluorine chemistry here, so I'm not going to go into detail, but you can activate this bond with fluorine anion, and then you can have the exchange reaction between this siloxane and this SEF bond. This chemical reaction is compatible with high temperature. It cannot require a catalyst, which is a source of fluorine, and so typically it's used with KF and polyether. And then you can do this potentially transform the polymer during processing into a vitumer and try to see if you can create good interaction at the interface. So in this work, they prepared PMMA vitumer using the amidification of the dependent ester, and this way they are crossing PMMA with this dynamic bond. They made a polyethylene vitumer using reactive processing and a very similar approach with a bismaleimide. And PP is much more challenging to transform by reactive processing, that's for sure, especially if you go for a radical process, because PP is undergoing beta fission, and this is something which is still a good challenge, I think, both fundamentally and in terms of application to be solved. I think there are, from my limited knowledge, there is not a perfect solution yet. So for PP, they use a similar approach, but they had to, it was necessary, to add this molecule, which is, you see, an accurate conjugated to a fluorine. The goal of this molecule is to react very fast with the radical created on PP to try to limit beta fission. I insist on the try to. And then you can go to have a PP vitumer. And they showed that, so they preformed this vitumer separately, PMMA, PE, PP, and they showed that if you blend these two materials in the melt by reactive processing, you can create a material with improved properties. A question you may ask, so I'm very critical to paper I read. I hope I'm also critical to my work. I'm not so sure about the interest of mixing PMMA and FGPE, and I don't consider this as a proof of concept because there are papers that were published before, among others from the same group, but I will come back to this. So if you mix PMMA and FGPE, you can go from a fragile material to something which has improved property. It's kind of ductile, but it's a good proof of concept. It's a very nice work. Don't get me wrong. I don't want to be too critical. And then here, one of the limitations, I would like to go back. One of the limitations is that you have to transform the polymer separately. And they are very well aware of this. They don't oversell. So the next step, which was done before, is can I develop a chemistry that I can use to functionalize at the same time, for example, HDPE, PP, PMMA, whatever I would like to recycle. And this is an important challenge in the field of mechanical recycling, but also in the field of polymer post-functionalization. So there are a lot of very nice work, and I'm not going to cite the initial work because the people that developed the graphene chemistry, so this aziridine, are different scientists. You have the work of Wood, you have the work of Leifert, but they are cited here. So if you are interested by this, read this, and you will go to the people that developed this chemistry for graphene. So the group of Eugene Chen, in Colorado, developed molecules that carry this aziridine, so it's a bisaziridine, and in the middle you have a bond which can be dynamic under certain conditions. So you have, for example, a disulfide, you have this acetate, you have this ester, which can undergo chemical exchange. And here's the trick, which is not a simple trick, is to introduce this group, which under the action of heat or light, will decompose, it will release nitrogen, and you create a carbene. And carbene, they are pretty reactive, as we can see, and they can insert into CH bond, and then you can more or less modify almost everything. So this is really the trick. Very nice work. Very nice work. I wish it would have been us. And you have also a work from the group of Shipping One, very nice. So the work I mentioned before. And here they use a bis sulfonylureazide, which can undergo decomposition under the action of heat or light to make a nitrine. So nitrine, they can also undergo CH insertion, but they can also do other things, as we will see. And in this case, they use their dynamic siloxane bridge, and this is a very nice example. In our case, so now I will focus to what we did in the lab. We were also interested in this type of nitrine grafting. We made a few examples before. And we recently shift our interest towards this type of molecule. So here you have a triazine core. This is aromatic with 3 nitrogen. It's pretty interesting because you have trichlorotriazine when you have chlorine here, chlorine here, chlorine here. It's very easy to make. It's used in a lot of applications, going from pesticide, but also it's a source of chlorine. So you can put this in your swimming pool to kill bacteria. So it is extremely inexpensive. But when I mean extremely inexpensive, it is really dirt cheap. And you can take advantage of the 3-chlorine to introduce more or less what you want extremely easily, as you will see. So this is a very nice synthetic platform to make functional molecule, and it has been here for a very long time. We are not the one introducing it. It's very well known. In this case, we introduce, and one of the positions, an azide, which can undergo decomposition under the action of heat or light. And then you go from here, and you make first species which is formed is a singlet nitride, where the 2 electrons are localized in the same orbital. And if you are here, you can undergo CH insertion and create an amine. Okay? This would be ideal for us. But what can take place after is intercrossing system. And when I say after, it's immediately. You create it. And if it doesn't undergo this reaction, in our case, it will go to a triplet state where the 2 electrons are in different orbital, and this is a biradical. And this biradical can act as a radical. It's pretty reactive, but not the most reactive, but pretty reactive. It can undergo H abstraction, so you can abstract this hydrogen, you create a radical here, and then the second radical, for example, or another molecule, can couple and you create the same thing. But the process is very different. And if you think about PP, so if you think about P, it's not so bad. You may create a bit of static cross-link because you will create a radical here that can recombine. But if you work at very low concentration of radical, this may be minimal. But with PP, you are going to go on beta scission. So ideally, this is what we would like to do. I would say ideally, of course. And again, the synthesis is extremely simple. So you start from trichlorotriazine. And when you want to make, if you really want, okay. What we do, we can make proof of concept, which is extremely nice. I have nothing about proof of concept. You create knowledge, you train students and postdoc and yourself as good as you can. And then sometimes you say, okay, but I think this can go a bit further, or I would like it to go, I wish. And I would like to go toward working with industrial partners to see if there is any type of potential. If you have this in mind, it's better to start with molecules that are easy to synthesize and not too expensive. It's not mandatory, but it will simplify your life to make the first connection with industry. So this is very available and expensive, and you go through a aromatic nucleophilic substitution, and you can introduce more or less any type of nucleophile you want. It's a very high Gadding reaction, no need for column chromatography, and then in the last step, you introduce the azide, and you can make large-scale synthesis relatively easy. I see Jean nodding. I'm going to go back to the large-scale part, but you can make a good amount of molecule very easily. What you should be concerned at this stage is that you see this molecule has a lot of nitrogen. So when a molecule has a lot of nitrogen or oxygen, among other things, but mostly this one, it has a high potential to be explosive because it will release O2 or N2, and this is liberating a lot of energy. So these are molecules that can be made or used to make explosive or propellers. So first thing, we had this in mind, and we, as much as we can, we try to not put the people that work with us under danger. So the first thing that we did is to study this molecule. So take a message, don't make a 15-gram scale to start, make a very small scale, few hundred milligrams or even less, characterize the molecule and see if it is safe to scale it up. This is what we did. So how we do this, we do typically TGA and DSC, and with DSC we can access a lot of things. So here in red you have the TGA, so you should look at here, so the mass loss. Here you have the temperature, and you can see that the molecule around 200 degrees Celsius lose approximately 10 weight percent, which correspond approximately to the weight percentage that you would expect if you use N2. Of course, under these conditions, the nitrine we make may be a bit volatile, so we expect to have a small loss. So this is compatible with the loss of N2, which was expected. And if you look at the DSC, we see that we have an endothermic peak here, which is the melting of the molecule, which is crystalline, so below 100 degrees Celsius, and a very highly exothermic peak here, which is the decomposition of the molecule. What is very interesting for us is if you want to do reactive processing by extrusion of P and PP, for example, you would like to have a molecule that will decompose above the melting temperature of your polymer to be processed. Otherwise, you will have to do it in solution or another way. The two examples I showed you before, they were done in solution. So I think it's a big limitation. And here, if you do this carefully, and this is well documented, has been done a lot, doing it at different temperature, different composition, you can access the kinetic parameter, you can access the enthalpy of decomposition, you can access at the order of the reaction, and you can assess if the molecule is explosive or not, and above which temperature you should not keep it on your shelf for a prolonged period of time. In our case, it's above 60 degrees Celsius, so it is safe to handle, but I really don't want to provide a bad message. We do multiple synthesis, we go up to 15 scale, and then we store the molecule in small batches. We don't have like a big can with 100 gram or 1 kilogram, which is ready to explode. This is one of the simple things to do. You store it in small volume. So molecule easy to make, which can be decomposed. And in our case, we did not know about the chemical reactivity nor the grafting reaction. So we perform model reaction either with only the molecule or we use paraffin wax, which is a good model for PE. It's a low molecular weight or very, very low molecular weight. PE, it's not a material, it's a wax, but it's much easier to analyze. You can do NMR of this, you can do GPC of this. Of course, you can do NMR and GPC of HDP, but it's a bit more challenging. So we use it as a model. We loaded it a lot so we can see what is taking place. We don't want to put that much additive later on the polymer. And we heated this and we studied what is taking place. And what we saw, I will go fast on this one, is that we formed small molecules, aminotriazine, for example. We formed also the azo compound, the hydrazine type compound, and also amino ether bridges. So a lot of different things. So it's not a selective reaction. The amount of this small molecule form really depends on the condition and the amount of additive added. But we also saw in bulk or even in paraffin wax that we are making high molecular weight structure. Persistent radicals that were identified by EPR and grafted structures. And if you look at the grafted structure, we really spend a lot of time analyzing them by NMR, EZMS, Malditor. We saw monograph. We saw monograph at the end, in the middle, and we saw also oligomeric graft with nitrogen bond, okay? Polyazine type of structure. If you want more details, read this very nice article. I'm very provocative to that. And then we went for reactive processing. First thing we did is PE. So we take a commercial HDPE. We don't make it. We don't know how to do this, unlike our colleagues. And we introduce between 1 mole% of additive to 0.05 mole% of additive. So here I will make a small break, and it's related to what Jean said at the beginning. So HDPE, you don't have to go to high molecular weight to have good mechanical properties. It's because if you think about the repeating unit of HDPE, it's 14 times 2, it's 28 grams per mole. So it's a very low molar mass repeating unit, which means that, in fact, when you are 3,000 or 4,000, you already have a lot of repeating unit, which is not the case necessarily for polystyrene, which has a slightly heavier repeating unit. I say this because if you put 1 mole% of this additive into PE, it is clearly not 1 weight%. So it is here. This 1 mole%, the molar mass of this is not 28. It's more like 200 something. 4% is 10 weight%, something that you should keep in mind, and I don't want to hide it. So there is a limitation to how much you would like to add, because if you add, for example, 5 mole%, you are close to a 50% weight% of P and your additive. Maybe it's no longer P, yeah? Something you have to keep in mind. So our process, we use a reactive extrusion, or it's not a real extrusion because it is an internal mixer with screws that rotate, and you have a recirculation channel. It's as close as we can be in our case from extrusion, but I do understand this is not a real extrusion. But we also did mono screw without recirculation with introduction at different stage. But here I will only discuss about this. So we go at 160 degrees Celsius above the melting point of PE. We introduce the PE. We introduce our triazine azide in a master batch because even though when it's a very low loading, it's difficult to introduce a drop of it. So we prepare a batch. Then we raise the temperature to 215, where the decomposition of the additive is extremely fast. And we run the reaction for 10 minutes. In our case, we chose 10 minutes because at 215, this is half-life time of the additive. So we decompose more than 97% of the additive. If we want to have more, we just go at 218 and we'll be at 7 or maybe 10 half-life times. And then this is what is taking place. I will have ready to rush, but I don't have the coffee break for me. So if you do DMA, dynamic mechanical analysis, so here you have the storage modulus or elastic modulus, because so elastic modulus, it was in elongation, so not storage. Temperature, our starting HDPE, as you would expect, when you are close to the melting temperature, in our case slightly above with the delay, the material flows under its own weight, and you can no longer measure an elastic modulus. And now, if we add a bit of additive, 0.05 mole%, so this is really not a lot, this is 0.5 weight%, you start to see, you can measure the storage modulus, and if you increase the loading, you have a storage modulus which is increasing, which we expect when you cross-link the material. The value of E prime on the rubbery plateau, if it's homogeneous, should be proportional to the cross-linking density. And in our case, we reach a plateau if we double the amount of additive from 0.5 mole% to 1 mole%, we don't see any change in the storage modulus. This is related, we believe, to the fact that our system is inhomogeneous. One point that I did not mention yet is that our additive, by design, is not miscible with P, and it is not miscible with PP. So I say by design because this allows us to have a very high local concentration of the additive. And in our case, we would like to make oligomers. If you want to make oligomers, you want this molecule to work together. So you want to have a very high local density. So if we go to a system which is homogeneous, which we did, either with the same molecule, different polymer, or different molecule, then we don't see cross-linking because they undergo hydrogen abstraction and grafting, and they don't have time to react together, or they don't have the opportunity. So even though I'm rushing, it's very important in our case to have a phase-separated system. But because of phase separation, there is a threshold. If you increase the amount of additive, you are not going to increase the apparent cross-linking density. So this is by DMA, and I will just repeat. We do it by reactive processing, reactive extrusion. So this is something that can be extruded, and in fact, it can be compression molded, and it can even be injection molded after. Yet, if we perform a creep experiment at 180 degrees Celsius, and we apply a moderate stress, we see that the material, so this is the one crossing with 1 mole%, but 0.5 mole% is the same. We see that the material above the melting temperature of HDPE, so when it is molten, so when it is not crossing, it is a liquid, is behaving as an elastic solid. We have an instantaneous deformation, and then when we release the stress here, we recover all the deformation, if not 0.0 small %, which led us to believe, and we did other things, that the crosslink we create, there are two types. There are first physical crosslink based on dipolar interaction and van der Waals interaction. And also we create crosslink which are polyazine, but this polyazine bond, we believe, can be thermomechanically activated. At high temperature and or under sufficient stress, they break and reform. And this is why we believe we can process our material. So our processing is not because we have a very fast exchange, but it's because we break crossing and we can reform them later. And in fact, probably often detremers, which can be processed in the melt, they are not dynamic enough so they can flow like this, but they just break and reform all the time. I think at least this is what is taking place with diisoborate. And within the 2 or 3 minutes that is left, if we crosslink, so this is a tensile test, starting HDPE, the same HDPE I showed you. So it's a ductile material, and now after crosslinking, of course, as you would expect, or you should at least, we significantly reduce the elongation at break. And we here by DSC, we show that we observed that we decrease the crystallinity, which in terms of mechanical properties translate in lowering the Young modulus. We cannot see it here, but it's a bit lower. It is phase separated, and we show this by TM, and the additive is is not dispersed in P before it reacts and after it reacts. And then I'm going to skip this. If we do the same thing with PP, because it is a radical process, we don't make a network, we just make a polymer chain of lower molecular weight because we make a lot of beta scission. But we were still able to show that we graft the additive onto PP and we still create our polyazine bond and we have radicals, as you can see by EPR. And I will finish with this. Now we can blend P and PP using the same additive at 1 mole%. We load both materials, then we introduce our additive, and then we heat to the processing temperature, which is exactly the same, and we do the extrusion. And in this case, if we look at the DMA, so this is the DMA of the blend of P and PP, 70% in weight of P, 30% in weight of PP. By DMA, if you look at the elastic modulus, when we reach the melting temperature of P, which is the majority phase, the material flows under its own weight, as you would expect. Now, when it is crossing with 0.1 mole%, we have the melting of PE here, we have the melting of PP here, and we can still measure an elastic modulus, pretty low. And if we increase the amount to 1 mole%, we can now see a rubbery plateau. So we were able to crossing the material. It is not fully crossing, but there is a chemical network in it. And if we do the same creep experiment at 180 degrees Celsius, this material is also creep resistant. So this is something which is really unusual. So it is highly colored. So for sure, you're not going to use it to make packages. And this would not be interesting for packages. But if you think about materials that require very good mechanical properties at high temperatures, such as construction pipes, this can be interesting. I'm not saying it's good, but it can be interesting. And then we studied the crystallinity. We can see radicals and the most important part for me at least, the tensile properties. Because if you do all of this and you don't have improvement of the tensile properties, it was pointless. So here you have the starting P, starting PP. This is a blend of the two without modifier. And when we do the reactive processing, it will come. We go back to ductile material. It is crossing, so we don't expect to have the same ductility. But we go back to material which has an elongation at break higher than 300%. It's an improvement of a factor of 10, in fact, more than 10 if you compare to the unmodified sample. And we really go back to a material which has very good mechanical properties. And this material is recyclable. Once you have made it by reactive processing, you can take the sample and reprocess it without undergoing reactive extrusion. You can just reprocess it, and you will have the same properties. You preserve all the properties. You preserve the tensile properties. You preserve the creep resistance, and you preserve the phase separation. So I knew it would be a bit long. So please, I would like to thank again people that did this work. So I really would like to emphasize the contribution of Nathan Vanzi and the different PhD students, so Thomas Vialon, Udison, postdoc, Paul Galanopoulos, and George Formont, and all our colleagues. And I would like to finish, because I really want to steal time, but with this thing, because it's related to what Jean said. So currently there is really a challenge to have, not currently, this is here for a very long time. In the field of polymer, often there is an incompatibility between improving the mechanical properties and maintaining a good processability, or improving the processability, not at the expense of mechanical properties. So this is something where we try to work on it, and this is purely proof of concept. So there is no application targeted here. But if you are interested, so this is something we apply, these are concepts we apply to bitumers, but they are not limited to bitumers. And these are two papers. So one of them is here, for example. So you have a polymer on which you introduce pendant function. That can be, I think, whatever you would like. You do this by reactive processing. And then here you have a crosslinker. But this crosslinker can aggregate through supramolecular interaction. For example, it can self-assemble and it can make fibers or colloids, which will be immiscible in the blend. So you have a dispersion of small molecules, but they are phase separated. And because of this, these functions which are compatible and complementary, they cannot see each other, so they cannot react. You process the material, keeping this hidden, you make the shape you want, so you process the thermoplastic, so good processability, and then only after you do the curing, where you will do chain extension. You can do simply chain extension. In our case, we did cross-linking, and post-curing, but with a very short step, you end up with a material which is crossing. And this can be decrossing and this can be recycled. And here it is more or less the same concept, but opposite way. So I wanted to show this to you. If you want to read, it's very recent. And now I will finish with this slide. And thank you very much for your attention.
Thank you very much, Renaud, for very inspiring talk and such incredible results. You share recent results. Thank you very much. It's really interesting. Are there any questions here, Patrick?
Thank you very much.
I have a question regarding your hydrogen therapy.
Yes. So regarding sensitivity to oxygen, I would not be able to answer because all the reactions we performed, so the model reaction were performed under nitrogen. And when we do the reactive processing, the material, and this is the way we put it in the lab, there is a fourth nitrogen. So we never try to do it without a plant of nitrogen, but reactive processing is done in the melt. So I don't know. In terms of replacing peroxide, this is something that can be investigated. And there is a lot of work in the community and people developing nitrogen-based radicals, such as UN, for example, not the only one. I think it's something that can be looked at, but probably it's not going to overperform peroxide. This would be my guess.
Thank you very much for your talk. I have a question regarding also this nitrate chemistry. So, is there a way to trap the singlet? And could you use like some kind of say like a Lewis acid to trap that and to make sure that you only have the desirable reactivity?
So I will give you a very honest answer for once. So we have been working on this, and but we are clearly not expert of nitrogen chemistry yet. So we played with so far we played with the substituents here and also the core, thinking that if we modulate the electron density on the nitrogen, we would be able to do this. So far, it was really 100% unsuccessful. But clearly, this is what we would like to do. So we don't have the answer, and we are very much looking forward to interact with people who have the answer. Regarding the Lewis acid, I really see what you mean, and it's when it is said it's pretty obvious. This is not something we considered, but now we consider it. But no, we did not think about it. But yes, we like this core a lot because of the simplicity. So in what we do in the lab, more seriously, our approach is we don't do very fine chemistry. We go for things that we can that can be scaled up. But yes, we would love to do this, and we were unsuccessful so far.
And just a question is that pure QLCT, did you try to make the triazide version of that?
No.
Okay. Because
no. And in fact, in the substituent we use, we were careful to bring enough carbon and hydrogen here to always be above the safety. One molecule that we are in the process of making, and once you have discussed this, it's obvious, is to make a diazide, but so we'll have two triazide which will be linked, and this can be of interest for many things.